It's now time to move on to the next mystery. So the answer to the second mystery was, actually the question first, one of Einstein's predictions of general relativity was not proved during his lifetime. About 30 years ago, it was observed indirectly, thanks to the observation of a binary star system. This result earned the Nobel Prize to two scientists who obtained the result. Today, many special antennas are deployed on our planet's surface to confirm this observation in a direct way and to study the phenomenon. So, Rolf, what phenomenon are we talking about?
Well, the phenomenon is called gravitational waves.
Gravitational waves. And what's special about gravitational waves? What are these?
Well, let's start with Einstein's general relativity theory, which sort of, in some sense, is an extension of his special theory, and in some sense extends it to accelerated systems, which he postulated and found out that there is a very deep connection between accelerated motion and gravity. These two sort of basically are linked. And so, in a nutshell, his equations basically predicted that the presence of matter, of mass, and energy would curve space. And this curvature of space then would tell other masses how to move. And so he gave a more extended explanation of Newton's gravitational theory, and he showed that, maybe the next animation will show that a little bit clearly. He showed how the curvature of space can explain the motion of, for example, planets around the sun. So I would call that, in a certain sense, that is a static picture of gravity.
So another mystery opened up by Einstein.
Well, in the meantime, I think that is very well understood, and general relativity explains a few effects which Newton's theory could not explain.
And we mentioned in the quiz there are special antennas trying to study.
Wait, I mean, we are not yet with the gravitational waves.
I mean, okay.
The gravitational waves now come in the second animation. Now you have to imagine that if you shake a charge, an electric charge, it emits radiation, it emits light. Yeah? So that is the origin of light waves, for example, when charges are moving. Now imagine the charge in gravity is the mass. Now, of course, gravity is a very weak force. So you need huge masses which move relatively quickly relative to each other, or the collapse of a massive star. And this event then produces a space curvature which sort of changes quickly and propagates like a wave. But that wave is basically sort of a ripple in space and time itself. And it is the gravitational waves that pose this mystery. We try to find them directly, but this ripple in space is a very tiny ripple in some sense. When you look at sort of the distance of, say, 1 meter, and you have a gravitational wave now deforming this 1 meter, the deformation would be only a tiny, tiny fraction of the diameter of an atomic nucleus.
So you need very special, very sensitive antennas to detect that.
Yeah.
And there are many antennas spread around, and I understand there is one even at CERN.
Yes, there is the Explorer experiment here at CERN, but I think there are many bigger and more sensitive experiments now being built or already in existence in the world.
One of them is in Pisa, and I have pleasure in connecting now officially with the gravitational observatory called Virgo. It's a European collaboration between France and Italy, and I have Carlo Bradaschia. Hello, Carlo. Welcome to Beyond Einstein. And you can tell us more about Virgo.
Yes, we are connected from the EGO, European Gravitational Observatory, near Pisa. And now I invite Filippo Menzinger, the director of EGO, to welcome you here in the observatory. Filippo.
Hello.
Good evening, Filippo. Welcome back to CERN.
Thank you. welcome here to everybody, to you and everybody hearing us and seeing us. I'm happy to welcome you to the European Gravitational Observatory, which has been set near Pisa by the French CNRS and the Italian INFN to detect gravitational waves. And to do this, as you may understand, we have to have a very special kind of equipment, a special telescope, very special because it's completely different from an optical telescope because, as you heard, gravitational waves are quite different form of radiation from visible light or other electromagnetic waves. For this telescope is called Virgo, is a gigantic interferometer with arms 3 kilometers long, and our task here is to have this telescope working, and for doing this we have got a staff of some 60 persons working here, plus we've got at any given time there are about 20 scientists that come from the 11 laboratories where some more 100 more persons are working, and the 11 laboratories that are in France and in Italy are those that have built this gigantic interferometer. And we have the purpose to handle this antenna or telescope and its connected technologies. There are very special technologies, and some of these are quite unique. We've got, for instance, very extremely stable lasers, one of the most stable lasers in the world. We have got the largest ultra-high vacuum vessel in Europe, totaling something like 7,000 cubic meters. And we've got a very special kind of seismic isolation, which is quite unique and very sophisticated. We are at the present in the situation in which we are commissioning the machine, which has been completed a couple of years ago, and we are commissioning to start the collection of data, which will start, we hope, during next year. And doing this, we are now showing you the control room around us, which is the place where the operator and scientists handle the Virgo interferometer by controlling all its characteristics and tuning up to achieve the best possible sensitivity. And just to end, I must say that EGO, the European Gravitational Observatory, has its purpose also to support research in for gravitational wave detection and theory of gravitational waves throughout Europe, with special programs like the R&D program and the institution of the Virgo EGO Scientific Forum. This to enhance the possibility of research, theoretical and experimental research in Europe and, of course, on site. Thank you very much.
Thank you, Filippo. Now I would like to invite Adalberto Giazzotto, who is one of the father of Virgo, to tell us something more about gravitational waves. Adalberto Giazzotto is a physicist from Pisa, and he started this research together with Alain Brier, a physicist from the Astronomical Observatory of Nice in France. Adalberto.
Okay. Thank you very much. I just want to give some idea on why we were starting at the end of years 80s to start with this enterprise, which is really something very outstanding because it is in some way the only way to try to reach observation of the universe in a completely different way. So we started I would say, 20 years ago with the project of this machine, and we decided to go on interferometer side. As you know, there are two kinds of detectors. There are the bar detectors and the interferometer detectors. The bar detectors in some way are short aluminum bar. One is in Geneva, you said before, which in some way transform the force produced by gravitational wave in electrical impulses. And these detectors have the characteristic of having in some way high sensitivity in some way narrow band. The interferometer works with the very long arms, and the long arm is dictated by the fact that the force acting on the masses, in this case are the mirrors, are growing up with the length, with the distance of the mirrors of the interferometer. So we went on the longest possible way we could do with the 3-kilometer objects, interferometer having two arms of 3 kilometers long. So we started this enterprise some 20 years ago, and it was approved in '93 by NFN and CNRS, and now we are in the commissioning phase. So this machine is, I would say, one of the most powerful machines in the world at the moment. There are the two American LIGOs, 4 kilometers long, and Virgo is a 3 kilometers, as I said before. And the idea is not to, the main accent of what we are doing is not to have the evidence of detection, which is, of course, a step necessary to go on, but to start gravitational astronomy. In some way, we think that this will be the big event in the astrophysics, in the world of astrophysics, when there will be the detection and the starting of the gravitational wave astronomy. Of course, this requires very big machines, very sensitive machines, more and more as the year passes. We are in design advanced detector in the United States and in Italy. And also Japan is starting thinking very sensitive machines. So this is something that I have the feeling that it will be not too long to have the first detection and then starting this gravitational wave astronomy. One of the targets we have, of course, perhaps will be the next generation, will be to observe cosmological radiation, cosmological background of gravitational waves, radiation, that this kind of detectors and this kind of radiation allow to go just, I would say, up to 10 to the minus 22 seconds from the zero time in the Big Bang. So this is the shortest, the smallest time reachable today with these incredible machines. So the idea is to open new windows in astrophysics. And as we open new windows with new radiation, it is sure that we will find extremely exciting things. Thank you.
Thank you, Adalberto. Now I would like to ask Heinrich Heitmann from the Astronomical Observatory of Nice to tell us in some more detail how Virgo will try to detect gravitational waves.
Thank you, Carlo. So, as you have heard, a gravitational wave deforms space. And this deformation of space works as follows. You have a separation of space, you have a stretching of space in one direction, and you have a squeezing of space in another direction. You can see this on the screen here. This is a little animation of the Pisa Tower. You can see the effect of a gravitational wave. Now, in our interferometer, we are using this effect for the detection. And how does this work? Now, as you have heard, we have 2 or 3 kilometer arms. And we are sending an ultra-stable laser beam on a beam splitter. This is a semi-transparent mirror. So we have a beam which is coming on this mirror and which is passing through in 50%, and 50% goes in the other direction. So we are creating now, in this way, two beams, and these two beams pass through the 3 kilometer distance which separates the central building with the beam splitter from the terminal buildings with the end mirrors. This beam path must be in ultra-high vacuum, because otherwise the beam will be disturbed by residual air fluctuations. And this, as Filippo has explained to you, is the reason why we have the largest vacuum system in Europe, consisting of 1.2 meter diameter tubes, which are long 3 kilometers. Now consider the mirrors. The mirrors must be of extremely high quality. They must be of such a good quality that we could not find any laboratory able for producing them, so Virgo has built a laboratory in Lyon in France for making these mirrors. They have an extremely low absorption, they have a very low scattering, and they have a very high reflectivity, which is of the order of 99.995%, which you can compare with the 80% of the reflectivity of a normal mirror. Now these mirrors send the beam back all the way of the 3 kilometers where they have come. The two beams then reunite at the beam splitter, and at the output of the beam splitter, this creates a superposed beam. It reconstructs a beam, which we can analyze, and analyzing this beam gives us extremely sensitive information about very tiny mirror displacements. So if you consider that a gravitational wave has passed, and that we have a small mirror movement at the, let's say, at the end of the north arm, where the mirror goes away from the beam splitter, then at the other arm, the mirror will approach a little bit the beam splitter. So it's a differential movement which we can sense in the interferometer output. And we are so sensitive that these mirrors, which are large like this, 35 centimeters, and which have a weight of several tens of kilograms, we can detect their displacement to a tiny fraction of the diameter of a hydrogen nucleus, which is really enormous if you consider the distance, the difference between the diameter of the mirror and the detection we can make. Now it is clear that if we detect such small displacements, we must be sure that that there is not, for instance, a truck which passes by and shakes the mirror. So the mirrors must be very well isolated against seismic vibrations. And for this reason, we have, this is a particularity of Virgo, we have very sophisticated seismic isolators, which are chains of coupled pendulums. So the mirrors are suspended in 10-meter tall towers, which carry these isolation chains at the bottom of which we have the mirrors. Now, you imagine we have a system of mirror suspensions, and these mirrors can now, if they are suspended, they can move as they want. And in order to avoid this, we have control systems, which are, of course, completely computerized. And these control systems we are supervising here in this control room, and you see the different monitors which give us information about the mirror positions, about the beams, and all about the status of the interferometer. And it's here that we are working every day in order to achieve the design sensitivity, and we hope that in a few months we will be able to be ready for detecting gravitational waves.
Virgo, can you hear me? We are running a bit late.
Yes.
And in 10 minutes we have an appointment with Fermilab in Chicago. We don't want to miss that. So can I suggest that we meet again at midnight? What about that? What about a midnight rendezvous with CERN and me?
Okay, why not?
Okay, thank you. So I say bye-bye for the moment. We have to give the solution of the third question. The third mystery was, it concerns one of the most important objectives of the LHC program. Two of the detectors will try to discover a new type of particle. Many of these particles may have been produced during the Big Bang and could be responsible for holding together the galaxies in the universe. What name has been given to that type of matter or to the particles? I think both answers are good for this third question. Just reveal us the two answers.
It's another dark mystery of the universe. The answer would be dark matter. But of course, I mean, I can explain here at CERN in the new LHC program, we are also going to find other things like that. I mean, at least we hope. And in some sense, the correlation between astronomical distances and the universe and the particle physics never became clearer than in the case of this dark matter. Because basically what we think it is oops.
Some jazz from Fermilab.
Yeah.
It means we
Hi,
get to
Fermilab.
go. Yeah, I know they have jazz. But anyway, let's go ahead
Yeah,
with this dark
well,
matter.
let me start maybe one step before. The question is, why do we think there is dark matter? Well, that is an old observation from about more than 50 years ago. Mr. Zwicky found it first, that when you look at galaxies, and then these galaxies, like our Milky Way, they rotate. And then you try to calculate how much mass is concentrated in these galaxies in the form of visible matter and all the other stuff which we know is there. And from that you can calculate the gravitational pull. But then you found out that these galaxies rotate far too fast to be stable objects if it was just this gravitational pull of which we know the origin. So basically the idea is that galaxies, all the galaxies in the universe are stabilized by a big halo of particles which sort of form the gravitational origin of these galaxies. And now we wonder, what are these particles? We have absolutely no idea right now. Of course, theorists always are a step ahead, and they say, yes, we have a theory here which is called supersymmetry, and maybe the lightest of these particles will be the origin of this dark matter. And if you do a calculation of actually what it is, how many of these dark matter particles should be around, then you look at this pot here, and you can see that all these, I guess, all the black ones are supposed to be dark matter particles. Maybe the density is a little bit high, but in any case, what that picture is showing is that there are many more dark matter particles on average in the universe than there is matter what we are made of. You know, so
Okay.
it's about 10 to 1 roughly.